the plan of the lecture is we would be as was discussed in the videos which I shared to you. I will be talking about disorder. Okay. I would not be going into much more discussion because Professor Murukar has already told you that the disorder which we have in mind, okay, the concept of disorder which we have in mind when we are discussing entropy is not the layman's concept of disorder which we use in our English language. Okay, so he had given you an example of two rooms, one room being uh, found in a particular order, okay, and the other room which was smaller, which was in a state of disorder. Okay, and he explained to you in the video that the notion that a room which is properly arranged, okay, with more number of things and a spacious room, that which we call it as order, okay, that is not the order which we are talking about when you are discussing entropy concept. Okay, so we would be discussing a bit about disorder, and in order to discuss this disorder, okay, I would be taking number of examples. Okay, smaller examples. You might find that some examples would be a sort of repetition, but nevertheless, because we want to be very clear on what is entropy, so I would be taking those smaller examples. Okay, obviously the concept of entropy which would be introduced to you would be via heat engine. Okay, so I would be discussing this concept of entropy via using the example of your favorite engine, that is a Carnot engine. Okay, so this is a different way of looking at entropy, and this by taking this example of Carnot engine, I would try to be very clear on, or I would try that you internalize this concept properly. Okay, so I designed a number of poll questions based on these concepts. Now, one is disorder and other on entropy. Okay, and this is to make sure that you have completely followed the videos. Okay, so let me put down a very simple question, and as I said, is that the plan is we would be evolving the concept of entropy. One is there are two ways of looking at entropy. The classical thermodynamics approaches to approach the concept of entropy via a macroscopic angle. That is, we are not bothered about what entropy means, but we would be looking at how the entropy was discovered. Okay, so the set of proofs which are there in the videos 3 and videos 4, okay, which leads to finally the concept of entropy from the macroscopic perspective, that would be taken later. But before that, I would be approaching the concept of entropy not in much detail, but to an introductory extent via the concept of statistical thermodynamics or microscopic thermodynamics. Okay, so for that, I have put a third question, which would, in a way, start the discussion. Okay, so in the third question, I want you to imagine. Okay, in the third question, I want you to imagine a piston cylinder arrangement wherein there is a gas. Okay, before introducing the question, I will be drawing that. So uh, I have in my mind a system, a thermodynamic system, which is a piston cylinder arrangement, and the working fluid is gas. Okay, working fluid is a gas. Okay, right. So this is a, you can imagine, for example, in your IC engines, internal combustion engines, petrol engine or diesel engine, this kind of systems, you would see that there is a cylinder, there is a piston which moves up and down during the processes, and there is a gas. Okay, gas in the sense that there is a petrol air mixture if it's a petrol engine, or it is a diesel air mixture if it is a diesel engine. Okay, so on and so forth. So this yeah, in a way you can relate to the real world also. Okay, so now I would be taking this example, and the third poll question is about this, that we are going to consider a piston cylinder arrangement, and in that there is a gas. Okay, So related to that, this is a question, and I'm launching this question. Okay. So what I'm talking about is the phenomena of expansion. You see that in the engines, your heat engines like petrol engine, diesel engine, you would find that there is an expansion of the gas and there is a compression of the gas. Okay. So in order to understand the concept of entropy and the usual processes which happen in the heat engine, okay, it is a good idea to relate the concept of entropy to what is happening in the real practice. Okay. So when you are talking about the gas in a piston cylinder arrangement, okay, I am asking you not about entropy. I am asking you about the concept of disorder. Okay, the molecular disorder. The responses, it is from the responses perspective. It appears that you are not very clear on what is happening there. Okay, I'm asking about expansion phenomena. Okay, and in order to answer this, you must relate to the example which was given in the video about the rooms. Okay, wherein there was a small room and there was a big room, right? So basically, when you talk about disorder in thermodynamics, okay, molecular disorder, the more is the system disordered, the positions of the molecules becomes less predictable. Okay, so when you are talking about disorder, we are basically talking about predictability of the molecule's position. Okay, okay. Let me close this poll and let me uh, try to answer this because it appears that about 50% of the class has not followed this. Okay, let me share the result. So the question was about piston cylinder arrangement, and the question was about the gas. Okay, the gas in the piston cylinder arrangement, and I am talking about a particular process. Okay, which you know that in real life, as I had given you an example of petrol engine and diesel engine, we would find that the gas is expanding and the gas is compressing. Okay, so what happens? Okay, what happens to the disorderness? What happens to the disorderness of the molecules when the gas is expanding? That is the question. Okay, so if you look at, let me hide this response. Let me hide this response. Let me answer this first. The answer is the molecular disorder uh, uh, would increase. Okay, there is a slightly there's a printing mistake in this. Sorry, typing mistake in this. Uh, the question has to be molecular disorder increases or molecular disorder decreases. Okay, so while typing this question, instead of disorder, I had typed it as order. Okay, but I hope that you had got that question. So the answer to this is that the molecular disorder would increase when there is an expansion. Okay, so let me hide this. Molecular disorder increases when there is an expansion. And are you able to see the whiteboard now, Gargi, or somebody? Okay, so you see that on the whiteboard, on the Abhijit, thank you. On the whiteboard, I have drawn a piston cylinder arrangement. Okay, so let us say that this is a piston and this is a cylinder. Okay, and I have assumed that there are only four molecules. There are four molecules which are present in the gas. Okay, so how many molecules are there? Let us say there are only four molecules in the gas. Okay, and now this gas, okay, this piston, this gas expands. Okay, so let us say that position was 1 initially, and now the position is 2. Okay, so the gas has expanded from 1 to 2. The gas has expanded from 1 to 2. So the system has moved from state 1 to the state 2, and this state 1 to the state 2, when the piston moves, right, so that is a process. Okay, when the gas moves from the state 1 to the state 2, we say that the gas has undergone a process. And what kind of process this gas has undergone? This gas has undergone an expansion process. This gas has undergone an expansion process. Now, if you look at the molecules, okay, if you look at the molecules of this gas, then when this gas was in the state 1, and let us say I wanted to predict this, let me call this as some 1A molecule, okay, or a molecule A, right? So when the system is at state A, okay, the system is at state A, then predicting the location of this molecule A, okay, molecule A is uh, relatively, okay, and I'm talking about relatively, is relatively easier than when we are talking about the state 2, the state 2. Because why? Because you see that now this has a more, this molecules have more space, okay, to move, right? So we don't know where this is. Okay, when there is a small space, then we can easily search for it. But when that space becomes larger, okay, when the volume increases, then it becomes difficult to search for it. Then it becomes difficult to search for it. Okay, relatively speaking, it means that the position of the molecules is difficult to predict. The position of the molecules is difficult to predict. It means that the disorder, the disorder is more, the disorder is more in the state 2 as compared to state 1. It means that when the system moves from state 1 to state 2, when the system moves from the state 1 to state 2, or the gas expands from state 1 to state 2, the molecular disorder would increase. The molecular disorder means in the state 1 also the molecules are in the state of disorder, but as compared to the state 2, the state when the molecular disorder is less, a state to the molecular disorder is more. So when there is an expansion process, the molecular disorder would increase. Molecular disorder would increase. So that is an answer, right? So I hope that you have understood this concept, that when we are talking about the phenomenon of expansion of gas, then it becomes difficult to uh, uh, predict the position of the molecules, okay, relatively speaking, okay, as compared to an initial case before expansion and after expansion. If you are comparing, then after expansion it becomes more difficult to predict the position of the molecules, okay. It means that the molecular disorder increases during the phenomena of expansion, okay. I hope you have understood this. So if you understood this, now let me ask a related question. Again, I have made a typing mistake. There has to be molecular disorder decreases and molecular disorder increases. Okay, I have made this mistake, I guess, in the hurry to. So please note that the options are molecular disorder decreases and molecular disorder increases. Molecular disorder decreases and molecular disorder increases. These are the two options, and not the options which are which you see in the whole question. Okay. Molecular disorder decreases, molecular disorder increases. What happens during compression? So just as I had argued, when you are discussed with phenomena of expansion, when you talk about compression, the volume would decrease. Okay, the volume would decrease, and the molecules would come closer. Okay, and then it would be easier to find those molecules. Right, when there is a space is less, then it is easier to predict the position of the molecules. So when you are talking about compression phenomena, then the molecular disorder would decrease. Okay, molecular disorder would decrease, and I guess that for looking from your responses, it is clear to me that you have all followed this. Most of you have followed this, right? That when you are talking about the phenomenon of compression, it's just the opposite of the phenomenon of expansion. So when there is a phenomenon of compression, when the piston comes closer to the top dead center, then the gases would occupy less volume. When the gases would occupy less volume, it means that the position of the molecules would become more predictable. The position of the molecules becomes more predictable. It means that the disorderliness would decrease. Okay, so when you are talking about compression phenomena, please note that the molecular disorder would decrease. When you are talking about expansion phenomena, please note that the molecular disorder would increase. Okay, so while there is an expansion, there is an increase in the molecular disorder, right? And why is that so? Because the position of the molecules becomes difficult to predict. When there is a compression, there is a decrease in the molecular disorder. And why is that so? Because the position of the molecules becomes easier to predict. Okay, so this you need to be very clear, I guess. And because 80% of the students have understood this, so I'm happy that you have understood, most of you have understood that expansion means there is an increase in volume and there is an increase in the molecular disorder. Compression means there is a decrease in the volume and there is a decrease in the molecular disorder. Okay, so let me close this question and let me show you the results. Okay, so you see that 80%, about 80% of the class has correctly answered this, that during compression phenomena, the molecular disorder would decrease, right? So let me hide this and let me go to the next question. And this is now because this small and subtle questions would help you appreciate the concept of entropy better. Okay, and I have not yet started with discussion of entropy. I am just talking about molecular disorder. Okay, so now I am talking about a different thing now. I am not talking about the phenomena of expansion, increase in the volume or decrease in the volume. I am going to talk about the phenomena of heat transfer. Okay, which is again a very important phenomena. If you look about real engines, for example, in petrol engines, you know that there is a heat transfer by combustion of the fuel, Okay, in the gas turbine power plant also, you find that there is a heat transfer by combustion of the fuel. If you are talking about the steam power plant, you know that coal is burned in the boiler, furnace of the boiler, and there is heat transfer. Okay, so all these practical examples which we encounter, they are basically the examples of heat transfer to the working fluid. Okay, so in this poll question, I have taken the working fluid as a gas, and I am talking about the phenomena of the heat transfer to the gas. Okay, and this what would happen to the uh, molecular disorder? Okay, what would happen to the molecular disorder when you are heating the gas? Okay, and this I am talking about. There could be two cases. One is you are not allowing the piston to move, and other is you are allowing the piston to move. Okay, there could be two cases. One is you are allowing the piston to move, or you are not allowing the piston to move. Okay. So let me close this and let me show you the result. Uh, the result is, you look at this question. I'm talking about the phenomena of heat transfer to the gas. Okay, and it's a rigid container, and about 75% of the students are saying that yes, when you are transferring the heat to the gas in the container, its molecular disorder would increase. And yes, they are right that about which 75% of the students are right, saying that when you are transferring the heat, there is an increase in the disorder. Okay, and I would be explaining you this a bit. Let me hide the question for the people. 25% of the students who are not answered it correctly. So I am talking about a rigid container. Okay, I am not talking about a piston cylinder arrangement. So when you are talking about a rigid container, it means that the volume would remain the same. The volume V would remain the same. The volume is not going to change of the gas. Okay, but what happens is when you are talking about heating that gas. Okay, so let us say these are the four molecules. Again, there are only four molecules in the gas, and this gas is enclosed in a container. Okay, you can imagine some vessel which is closed from all the sides, and no walls of the vessel can move. Okay, it is a rigid container. I'm not talking about a piston cylinder arrangement. Okay, so in that case, when you are talking about heating this, what would happen is there will be increase in the temperature. There would be an increase in the temperature of the gas. Okay, and this temperature increase uh, of the gas is because the internal energy of the gas would increase. And what would happen if you try to focus on what happens at the microscopic level, that is what would happen to the molecules, you would understand that these molecules will start jumping. Okay, they would start jumping. Okay, so it means that when these molecules are set into motion because of heat transfer, and this heat transfer, because there is heat transfer, the volume is not allowed to be uh, allowed to change. That is resulting in the increase in the internal energy, increase in the temperature, and from the microscopic perspective, the randomness of this molecules will increase. Okay, so when the randomness of this molecules would increase, it means that when this molecules are relatively more randomly dancing. Okay, these molecules are relatively more randomly moving, then the position of these molecules would be relatively more difficult to predict as compared to the case 1. Okay, so case 1 is without heating, and case 2 is with heat transfer. Okay, please note that I have considered the volume to be constant. So when you are heating the gas which is in a rigid container, that results in the increase in the temperature, and that results in the randomness of the molecules. So there will be more randomness, there will be more disorder. Okay, there will be more disorder. It means that it would be and you can easily visualize that when these molecules are dancing, okay, so it would be difficult to locate these molecules, it would be difficult to locate the position of these molecules, and that means that these molecules are at a higher degree of disorder as compared to the case 1. These molecules are at a higher degree of disorder as compared to the case 1. In other words, when there is a heat transfer, there is an increase in the molecular disorder. Right now, if you take a second case in which, for example, you take a volume which can expand. Okay, volume which can expand, right? And if you are transferring the heat, and let us say that this heat transfer results in the piston moving towards the state for 2. Okay, so there is a state 1 and now you have state 2, right? So yeah, cooker is an example, Vedant, that is correct. But cooker, when the whistle is not moving, okay, when the whistle is not moving, then the cooker becomes an example of a rigid container, right? Okay, a closed system. Now if you take a piston cylinder arrangement, and now if you are having a heat transfer, and you don't want the temperature to increase, but you compensate that change in the internal energy by allowing the piston to move to a state 2, so you are having a heat transfer, but let us say that this heat transfer is isothermal. Meaning what? The meaning is you are allowing the temperature to remain constant while the gas expands. Okay, and this movement from state 1 to state 2, what would happen to that? Whether the molecular disorder would increase or not. Okay, so in this case also, when you are having a heat transfer, and the vessel is not a rigid container, but it's a piston cylinder arrangement where the boundaries can move and the gas can expand, here also the molecular disorderliness increases. And why is that so? Anybody can answer this? Why is that so? That in spite of the fact that the temperature remains constant, the molecular disorderliness would increase. That is because why? Can somebody answer this question? Okay, ठीक है. That is because the volume would increase. And because the volume would increase, it would be less. Yeah, correct. Tanaya is right. The volume would increase, and because the volume would increase, it would be difficult for us to predict the position of the molecules. Okay, it would be difficult for us to predict the position of the molecules, and that means the molecular disorderness would increase. Okay, I hope this is very clear to you, and if this is clear to you, I don't find it very difficult for you to answer the next question. So let me launch the next question. So this is about, again, heat transfer from the gas in a closed rigid container. Think about the question. Read the question very carefully. Okay, I'm getting very wrong answers for this question. So don't be in a hurry to answer the question. Read the question carefully. before you answer it. So I'm talking about exactly the opposite phenomena. Okay, I'm talking about exactly the opposite phenomena. That uh, that there is a heat transfer from the system to the surrounding. There is a heat transfer from the system to the surrounding. In the earlier problem, what I had discussed was, in the earlier case, I had discussed that there is a heat transfer from the surrounding to the system. Now, what I'm saying is that there is a heat transfer from from the system to the surrounding, from the system to the surrounding. It means that there is heat loss, and there is a heat loss, and because there is a heat loss, again using the same argument which I had. Okay, same argument which I had. If it is a rigid container, the temperature would decrease, and if it is a piston cylinder arrangement, there would be a compression. There would be a compression. Okay, in either case, the molecular disorder would decrease. Okay, let me repeat this. Just think of it as an opposite to the case which I discussed. Okay, in the case which I discussed earlier, I was talking about the heat transfer to the system. Okay, and I discussed two cases. One was a case of a rigid container, and other was a case where the piston is able to move. Okay, the piston is able to move, and the gas would expand. Gas would expand. Now I am talking about exactly the opposite case, wherein there is a heat rejection from the system. And when there is a heat rejection from the system, then in the case one again, what would happen is the temperature would fall down. The temperature would fall down. Or in the case two, what would happen is, if I want to make sure that the temperature does not change, the process remains isothermal, then what would happen is the piston would have to compress the gas. Piston would have to compress the gas. Okay. Yes. स्पेस कमी होता है असं कोण लिहित आहे गार्गी इज हॅव्हिंग सम क्वेश्चन पण सर गॅस हा मोठ्या व्हॉल्यूम पासून लहान व्हॉल्यूम कडे जातो आहे वी आर नॉट डिस्कसिंग एंट्रॉपी सो डिग्री ऑफ रँडमनेस correct, that is what I am saying, that degree of randomness would decrease. Okay, same thing which I am saying, Gargi. I am not saying anything different. When you are talking about heat rejection, I am saying is that the randomness would decrease. Okay, I am saying the randomness would decrease. Okay, same thing which you are saying. I am not saying the randomness would increase. The molecular disorder would decrease, which is what most of you are answering. Okay, let me close the poll and show you the result what students are saying as answer. Consider the heat transfer from the container to the surroundings, the molecular disorder would decrease is the right answer. Okay, which 65% of the students have answered it correctly. Okay, that the molecular disorder would decrease, right? Okay, I hope it is very clear to you now that whenever there is a heat transfer from from the system to the surrounding, the molecular disorder would decrease. Okay, the randomness would decrease, right? I'm hiding this and I'm going to the next question. And now what I would be doing is that I would be relating this entropy with molecular disorder. Okay, we all know that entropy is a measure of molecular disorder. Okay, and now this would be a sort of repetitive questions, and this would help you appreciate better what is entropy. Okay, so let us take one by one, and this would be very interesting to answer, and I'm sure you would be answering it correctly. Okay, so let me talk about now the first question, which is about expansion phenomena. Okay, expansion phenomena. I'm sure most of you should answer it correctly. So we are talking about expansion phenomena, and now I'm not talking about molecular disorder. I'm talking about entropy of the gas. So when there is an expansion of the gas, okay, in the piston cylinder arrangement, when there is an expansion of the gas in the piston cylinder arrangement, right, what would happen to the entropy of the gas? So you need to answer it very fast. Only 20% of the students have voted. Let me close the poll and let me see how many of you have correctly answered. About 80% of the students have answered it correctly. Can you see the whiteboard? Okay, thank you, Vedant. What I have shown is the phenomena of expansion. Look at this. There is a piston cylinder arrangement. There is a gas. The piston was initially at a position 1. Okay, position 1. And after it expands, it goes to a position 2. Okay, and as a result of which the gas is expanding. So as I had explained you, this phenomena of expansion would lead to an increase in the molecular disorder. The predictability of the molecules would it would be more difficult to predict the position of the molecules. That is, the molecular disorder would increase when the gas expands, and the entropy of the gas would increase. It means that whenever we are talking about expansion phenomena, the entropy would increase. Okay, 80% of the students have answered it correctly. Now let me go to the next question. Okay, so as you see here, that 80% of the students have got it right. Okay, I'm closing the poll because I have one or two more polls to discuss. So you have followed that when there is a heat transfer to the gas, okay, there would be increase in the disorderliness. Okay, when you are transferring the heat, you are seeing the whiteboard, and I have shown that there is a piston cylinder arrangement. Okay, or you can even imagine a rigid container. Okay, so I am showing that there is a heat transfer from the surrounding to the system. Okay, so along with the heat, okay, as I had explained you, along with the heat, the disorderliness would be transferred. Okay, in a way you can think of this in this manner. Okay, you can just think it this way, that when you are transferring the heat to the system, you are in a way transferring the disorderliness into the system, or you are in a way transferring the entropy into the system. So along with the heat flows the entropy. So when there is a heat flow into the system, there is a flow of entropy into the system. Okay, there is a transfer of entropy into the system from the surrounding, and the entropy of the gas would increase. Okay, so when you are transferring the heat from the surrounding to the system, there is a transfer of entropy, there is a transfer of disorderliness into the system, and the gas would be at a higher state of molecular disorder. The entropy of the gas would increase. So